In this video, we're going to take a look at how you can start applying these quadratic functions to a more real-world sense. And in order to do this, we're going to be looking at problems where you're either looking for the maximum or the minimum. And these are kind of neat because you can use your ideas of the vertex in order to find the maximum or minimum. In our first problem, we're given that the height h of a punted football is given by the following quadratic equation. Here, y represents our height, and x represents the horizontal distance in feet from the point at which the ball is punted. Now, what we want to figure out with this is basically just answer a few questions. We want to know how high the ball is when it is first punted. And we also want to know what is the maximum height that the ball obtains. Well, in order to start answering these questions and to even see why a quadratic would be appropriate, let's take a look at what happens when you plot out the equation itself. So I've made like a mock-up of a football field where x represents the horizontal distance and y would represent the height in feet. If you graph out the equation itself, you can see that it follows the path of a punted football. You know, it'd go up in the air and then eventually come back down. And what we're interested in is really figuring out where's the vertex of this parabola. So where is that maximum point? And we're also, curious about, what is the height of it when x is equal to 0, when it's very first punted. To figure out the first question of how high the ball is when it's first punted, we can think of this being where x is equal to 0. That's because at this point it hasn't traveled in the horizontal direction any distance whatsoever. So by plugging in x equals 0 and then just simplifying it, we get a height of about 1.5 feet. So basically someone's holding it about 1.5 feet off the ground when they first kick it. Now for the second part of this, we need to figure out where the maximum height is. Well, we can use our formula for the vertex of a parabola, negative b over 2a, in order to find this point. So I'll plug in the 9/5, that's the b, and the negative 16 over 2025 for the a. Now this does take a little bit of simplifying. I had to, say, multiply the part on the bottom, and then flip it and multiply by the top on by the part on the top. Now, when I was all done, I got something like x was equal to 3,645 divided by 32. And keep in mind that that is not the maximum height. X represents our horizontal distance, so this is just how far the ball has traveled before it reaches its maximum height. In order to figure out how high the ball really went, we would plug this into our function and see what we get. Now this is probably a good idea, or at least a good spot to pull out your calculator and see what value you get. I did that, and I got that my y value was equal to 104.02 feet. So that represents how high the ball was at the maximum. In our next example, we're going to have to start building our quadratic equation from some certain bits of known information throughout the problem. In this one, we have an indoor physical fitness room consisting of a rectangular region with a semicircular track on each end. Now, the perimeter of the room is to be a 200-meter single-lane running track, so it'll run around. And the dimensions, well, we want the dimensions of the rectangular area to have a maximum area, so to be as large as possible. So a good description of what I'm talking about is this. The pink area represents, say, the physical fitness area, and then the green area around it would be the track. And I must have that track at 200 meters, but also keeping in mind that I want as large of pink area as possible, so maybe I could put in some other type of equipment there. Well, in order to figure this one out, I have to build my quadratic equation first. So I start tacking down some knowns from the problem to see if I can build it. And one of the first things I can start to build has to do with the length of that track. Keep in mind that since it has two semicircle pieces on the end, that if I put those two together, I have one circle. And that the radius of that circle would be something like y divided by 2. So the entire perimeter of just the track itself would involve, say, the circumference of that circle, 2 times pi times r, plus both of the straight pieces, so 2x pieces. Now we want to make sure that this represents the track when it is exactly 200 meters. So I'm going to plug in the 200 for p, and I'm going to plug in the y over 2 for r. And this will simplify down into 200 equals pi times y plus 2x. So just this equation right here represents the length of that track. Now I'm going to go ahead and solve this for y, so I can plug it into another equation in just a bit. The other piece of information that I'm really interested in is going to be the area of the pink region. So area would be x times y, or length times width. And what we're looking to do is maximize that area. Well, right now I have area in terms of x and y, so two variables. And I have the length of the track in x and y as well, so again, another two variables. If I put these two bits of information together, I can form a quadratic equation. So I've substituted the perimeter into the area formula and basically swapped out the y for the 200 minus 2x divided by pi. Now that might not look quadratic, but if you distribute the x, sure enough you can see you get an x squared in there. So I have that the area is equal to a negative 2 divided by pi times x squared plus 200 divided by pi times x. And there's our quadratic equation for the area. Now we're really interested in where this has a maximum area. So I could use my formula, negative b over 2a, to figure out what the length of x needs to be in order to achieve this maximum. I got that this happens when x is equal to 50. Now if I know that x is 50, I could actually plug this back into the perimeter and figure out what y needs to be. And then once I know x and I know y, I can figure out what the maximum area of the track is.